All right. I want to thank two of my colleagues for helping me put this presentation together. Anastasia Laety at Caltech is the system engineer for COA, and she also helped with putting together the TAP slides, which I'll show you later on. And Jeff Mader at Keck Observatory is the manager of the Keck Observatory contribution to COA. All right, so let me begin by stating the problem. Now, the ultimate goal of COA is to turn this enormously successful and very large privately funded telescope into a public resource and thereby maximize the science return that you can get from the observatory. Now, to do this properly means that the data have to be fully self-describing so that archive users who are not Keck principal investigators and Keck observers can actually understand the data. So that implies we have to have a very complete set of metadata that are consistent and fully documented. Now, historically, the observatory invested in glass, silicon, and metal rather than in the back end and providing services and consistent set of reduction pipelines for observers. Essentially, when you got your data, it was up to you what you did with them. A consequence of this was that the instruments, and at the moment there's 10 active and 2 decommissioned ones, they were all developed by multiple teams. There was not a lot of coordination between them when they were being built. And a consequence for the archive is that there's a really heterogeneous set of metadata. And that was the problem that we were dealing with. Now, the observatory itself began operating in 1994. The data were stored, kept in a warehouse at Keck in a digital tape farm. Later on, the data got written onto DVDs as well. Now, the observatory archive, COA, itself opened for business 10 years later in 2004. And when we opened, we were serving only data from one instrument, HiRes, which is a very high resolution spectrograph. And we were only serving data which were freshly acquired from 2004 onward. Now, we added new instruments, the newly acquired data from the additional instruments one by one through the years, and that step was completed in 2020. And once we had the newly acquired data archived, we went forward, ingesting them night by night. Then we went and backfilled all the earlier data. That was the broad process we were using. Now, the volume of data by modern standards is not that large. Currently, we're standing at a little over 70 terabytes. But the issue here, excuse me a second, is that the instruments are really complex. And as a result of that, the data and the metadata are also highly complex. Now, we give you an example. The HiRes instrument I just mentioned has 417 keywords in its FITS header. MOSFIRE, which is a multi-object spectrograph optimized for use in the infrared, has even more. It's got 578 keywords. So what did we do about this? Well, there's a paper we wrote in 2014, which is published in SPIE. You can see the front page on the right-hand side there. Describes the overall processes. Although we didn't complete things until 2020, the methodology is still sound. So I sent that paper across to Wendy, and it can be freely distributed. Now, so what we did was perform an analysis of the metadata instrument by instrument, as we mentioned, between 2010 and, I should say 2020, not 2010 to 2010. Sorry, my mistake. We analyzed the metadata for completeness, consistency, allowed range, whether there was documentation on what that metadata meant. In some cases, it was fairly self-explanatory. In others, particularly for instrument parameters, It wasn't. You'd have parameters, for instance, for high res, you'd have things like XC3R74, which actually refers to a temperature of the CCD. So all that had to be documented. We updated the metadata in the data files. And then we provided the end user documentation on metadata as it was needed. And the final step, we created master spreadsheets of all the metadata containing all the fields. It identifies it, the origin, whether it's produced at the telescope, whether it's observatory specified, whether it comes from an instrument, whether it's added by COA, and so on. The data type, the allowed ranges, and sample values. Now, there were three broad types of problems that we had to attend to. Not every problem occurred in every instrument, as I'll describe with some specific examples later on. Nonetheless, there were three broad types of problems. One is that the type of data is not identified in the FITS files. Usually you know whether it's calibration science, but not always. But often you don't know whether it's a calibration file, a doc file, a flat, or a sky. The observers did because they wrote it down and they had that information when they analyzed the data, but it wouldn't be available to a third party who wanted to work with those data. Secondly, the WCS information. Are you familiar with WCS, the World Coordinate System? Specifies essentially the footprint of the detector on the sky. That is often missing or incomplete or unknown. And finally, there were a collection of oddities and inconsistencies in the keywords themselves. Now, I'll give you some examples of those a little later on. So the metadata analysis we found had to be done on an instrument by instrument basis. The instruments differed sufficiently. We got very little economy of scale. And we could not come up with a fixed my metadata toolkit that we could apply quite generally, although we had hoped at the beginning we'd be able to do that, but it turned out there was so much variation from instrument to instrument that it would have been very hard for us to do that. So let me give you some examples here, and after the examples I'll give you some statistics on how many files we had and how many they were corrected. OSIRIS here is one of the most widely used instruments at Keck. It stands for OH Suppressing Infrared Spectrometer. It's a 3D spectrometer. You take an image on the sky, and for each pixel in that image, you get a spectrum. And it turns out we don't know the type of the image that was written into the FITS file. We knew that it was one of two types, an imaging file or a spectroscopic file. Those are the two modes that it operates in, and that is written into the FITS header, but we didn't know anything else. So we set up an algorithm here that's encapsulated in this diagram. I won't go through it, but that's what we developed, and we applied it to every single OSIRIS file. Another problem we had is that we didn't know whether we were looking at the sky a lot of the time. So again, we set up our own particular custom algorithm to loop through all the files and find out which files were pointing at the sky, and in some cases you can use the dark current with the shutter closed as the sky. We identified those as well. And in some cases, we couldn't identify at all. See that right at the bottom, no sky. There was a few cases where we couldn't identify the type at all. So no, the end users on their own, I'm afraid, there's no way that you can reliably do the data reduction with the standard reduction program. So another instrument, this is called NURP2. It's a near-infrared camera. It's a very sensitive camera for looking at the sky in the very near infrared. Now, historically, it didn't contain information on what calibration lamps were turned on, but we were able to come up with an algorithm by looking at the pixel data themselves. And the three images at the bottom show you the differences in the type of data that get recorded for three examples there: the flat map off, the flat, and the arc lines. So WCS, now this was a real problem and one which we never completely solved. In some instruments, such as KCWI, for example, and MOSFIRE, the WCS information is computed at the telescope and written into the FITS files. It's not the case for most of the instruments. So we had to do an analysis and determine whether we could find this information, how reliable it was, or identify where we couldn't do the calculations reliably at all. And as you can see, there's a number of instruments where we're not able to do that. We provided a very thorough set of documentation for users on this for every instrument. We went into the algorithms we used, which differed considerably from instrument to instrument, and some indication of the quality and the reliability if users wanted to take advantage of them. This is an example for one instrument. This is the kind of documentation we provide. This is for an instrument called NurseSpec, which is a near-infrared, very high-resolution spectrometer. So let's move on to the oddities. There are a lot of these, it turned out. In some cases, there were missing vital info, like the UTC, the universal time of the observation, the RA in the deck, the position on the sky, and the data obs, which is the date of the observation. So we were able to recreate that using date and time stamps, actually, that were in the directory and the ancillary files that were written at the observatory, but were not transmitted to the archive. And for some calibration files, we were able to actually calculate the UT timestamps ourselves. Sometimes we came across a lot of duplicated keywords. In that case, we verified with the observatory that they were true duplicates, and we only needed to read and ingest the very first one. Sometimes we found things such as unknown and null or really wild values in the keywords. In some cases, they were caused by a server crash, which just populated the files with junk. But we were generally able to populate the files with the values that we got just before the crash. Sometimes you just accepted the null because it might actually be valid. And so sometimes we had to adjust the range of keyword values. We did this on a case-by-case basis, but we always did this in consultation with the instrument specialists at the observatory, make sure we weren't making any bad mistakes. There was no file naming standard in the files. In fact, file names were replicated from night to night, which would cause immense confusion in an archive. So we created our own naming convention that would always encode a unique file name, and it was the instrument followed by the time of observation. I give you an example there. DE stands for the Deimos instrument. It's a high-resolution spectrograph, and the numbers you see behind it are the UCT time. And finally, the program information that identified who the observer was and what the program number was often incorrect on shared nights, so we had to analyze all those nights and correct the information. So let me give you a couple of examples to give you a sense of the kind of work we needed to do. So with the OSIRIS instrument I mentioned earlier, it turned out that I'm sorry, I hope this isn't getting too technical, but I think this is highly illuminating for the kind of work we had to do. We found that the script that took the dark observation for OSIRIS turned off writing the telescope drive system and adaptive optics keywords into the headers. Now, dark frames are often taken during the day, so you don't have to know the status of the telescope necessarily. But there was one big consequence to that, is that headers didn't contain time information. So what we were able to do was calculate them ourselves. We started with the UT midnight of the day the files were taken, and then used the known exposure times, which we did have, and estimated the times of the observations and wrote those into the FITS files. Another example, shared nights, which could be a complete disaster on some occasions. This is an example for Mossfire. Now, the way Keck allocates time, a not insubstantial number of nights are shared. One observer gets half the night, and another observer gets the second. This will actually become more common in the future when telescopes such as the Rubin Observatory are commissioned, and there'll be a lot more transient astronomy, time-dependent astronomy, so there'll be a lot of on-the-fly observations at the observatory. So what we found for Mossfire was that the program name and the keyword were either wrong or missing, and we essentially came up with this algorithm here and went through all the steps to try and identify correctly who the observations belong to, and corrected the observations. So I'll give you a sense of the statistics for Mossfire. I'll just read the top one. So 74 science files in this program K177M went instead to K128M, not in substantial number. 213 Cal files went to K128 instead of K177M. And finally, there's actually a bug in our own program called PyDEP, which prepares the data for ingestion into the archive. We had a bug in that, so we had to change the way the naming convention for directories were set up. So let me give you an overall sense of how common this kind of problem was. Giving you an average number doesn't mean anything. The statistics vary enormously from instrument to instrument. The total number of files we had to process were to date about 4,400,000, which is the total number of science and calibration files in the archive. Now, every one of those had to have a unique file identifier and other archive-specific information written to them. Now, aside from writing these archive-specific keywords, the files that required correction did vary a lot from instrument to instrument. So for the OSIRIS and NERC2 instruments that I mentioned earlier, we had to correct 100% of the files because every one of them had image typing information missing. So that was an extreme case. Now for Mossfire, we corrected about 25% of the keywords, which was a rough average for most instruments. The bottom of the list there, you see the low end, which is ESI, which is a shell spectrograph. By Keck standards, that's actually a very simple instrument with a corresponding simple set of metadata. In that case, we only correct about 7% of the total files. All right, so let me move on to something else, because we have talked about the TAP service. Once you have all the metadata into the archive and served to users, right, that's one part of the process. Once we build our TAP service for VO compliant, we had to go through setting up schema for the TAP service. It was an additional process that we needed to go through. So we have actually built at Nexsign a Python API, a server, Nexsign TAP, that provides compliance with the table access protocol. Nexsign TAP is written in Python. I think it's the only TAP server in astronomy that's fully written in Python, to the best of my knowledge. Now, the protocol itself defines it. At heart, it's very simple. The details are very complex, but defines a web service that allows you to search tables in relational databases using a dialect of SQL optimized for astronomy, particularly spatial queries, called the Astronomical Data Query Language. Now, the protocol page, which I've shown on the right, is actually a fairly long document, do define what the schema have to look like, and it's very strict about it. This gives you a little more detail about Nexsign TAP. As I mentioned, it's in Python. It's actually pretty compact. The Python itself is only 10,000 lines of code. It is freely available on our GitHub repository, and it's been released with a BSD 3-clause license. So this next slide gives you a sense of how we set up the database infrastructure. So Nexsign TAP could read it and serve the data back to the TAP client. There are a number of challenges in this. We do not want the TAP application having access to everything in the project schema. There is information there on observers and such, and release dates that are not intended for general consumption. Sometimes we found we needed to hide or rename certain columns, like we were not going to put the release date out, for instance. And the schema name, you have to pass them directly to Oracle by Nexsign TAP. Now the solution, we set up multiple schemas as well as views and synonyms. In future, we'll probably allow the TAP schema to be an alias that's going to be controlled by a TAP configuration file. We realized after we'd done it, that was probably the best way to go about it. And the diagram on the right-hand side gives you a cartoon on how those schema were set up so that we're TAP compliant. There's quite a bit of work went into this. Anastasia did the bulk of the work. She found that getting this thing set up and for the very first instrument took about 6 weeks of work. But since then, she's been able to automate the process. And assuming we have a stable set of metadata in the database, she can now create a TAP schema for testing within a couple of hours or so. So there are 2 slides here which I decided not to go through because they're very highly technical about how we set up the TAP schema. So if you're interested in the details, please, and if you have questions, let me know. Okay, so let me just go to, oops, I'm sorry, private final slide. Okay, this is a sort of happy benefit we got from developing the TAP service. We're actually able to develop a much cleaner approach to managing our metadata and driven by instrument keyword tables, one for every instrument that we actually put in our GitHub repository, and everything, all the various components that needs to have access to the keywords can go through that. It's made our lives somewhat easier in managing the operations in the archive. So that is the end of that presentation.